So if you want, you can start sharing your presentation, and I'll give a brief bio of Gustavo. Okay, so can you push play there so that we see?
I was muted. Okay. Okay.
Perfect. Perfect. Okay. So Gustavo did his PhD at the Instituto de Astronomía, Geofísica y Ciencias Atmosféricas de la Universidad de Sao Paulo. He was supervised by Rodrigo Nemen. And in his PhD, he worked with characterization of laser emission, as well as particle acceleration in relativistic jets. During his PhD, he actually was a visiting PhD researcher at Northwestern, I guess with Sasha, no?
Yes.
I guess.
Yeah.
And then since March last year, he's a postdoc at Oregon State University, OSU, with Davide Lazzati. And so Gustavo's interests are GRBs, especially the formation of jets, as well as their interaction with different environments. And he approaches these problems using mostly 2D and 3D large-scale numerical simulations. Also, he does a lot of divulgación, and he has students in licenciatura and postgraduate. And I also read that during his free time, he does rugby. So yes. Be careful. Let's
yeah,
be careful.
I once had a serious injury, so I know how it feels like.
Okay, so with this, welcome, Gustavo, and it's all yours.
Okay, thank you, Diego and Leo, for inviting me to talk a bit about my work here. Yeah, so as you can see, and as Diego has already said, I work with gamma ray bursts. What I'm going to present here are two projects that I'm currently working on. One of these two projects is almost finished. We just have some extra analysis to do and finish writing this paper. The other one is more or less 70% finished, but we really do expect that by mid-July or so, both papers will be already submitted, and perhaps even one of them could be accepted. So yeah, these works that I'm going to present here are done in collaboration with a couple of people. They are Pablo Bosch and Philip Musta at the University of Amsterdam. There's Davide Lazzati as well here at Oregon State, and we are also working with Rosalba Perna at Stony Brook. So let me start just by giving you a very brief outline of what I plan to talk about here today.
Sorry, I forgot, Gustavo. I forgot. If we have questions, do you want us to ask when they come or until the end of the?
Yeah, sure. You can interrupt me and ask me questions whenever you want.
Cool, thanks.
So yeah, I'll start with some very general context. I know that some of the things that I'm going to say here are things that you guys surely know. Like, there's people here who work with gamma ray bursts, so there's nothing new. I'm going to show some like a cartoon of sorts that I know everyone has seen before, but I'll try to keep that a little bit brief. And then I will follow with two more parts in this presentation. First, I'm going to present one of the projects that I'm working on in collaboration with Philip and Pablo in Amsterdam, which is a project where we investigate magnetars as a possible source that powers gamma ray bursts. And as I talk about this project, I'll give some extra context, some extra motivation. And then after presenting our main results, I will talk about another project that I'm working on, which concerns the environments in which gamma ray bursts might appear. In particular, for this project, what we are interested in doing is, and we are investigating what could happen if a gamma ray burst originates in a very dense environment, such as the accretion disk of a supermassive black hole. So let's start with some very general things that I think everybody here knows. So I'm going to talk about this photo in more detail, but gamma ray bursts, they are explosions. Their energies are extremely high, like 10 to the 50 ergs, sometimes even a little bit more. They occur upon the death of a massive star, which leads to a supernova, or they might occur as well upon the merger of two neutron stars. So they are classified within between short and long gamma ray bursts. Short gamma ray bursts last for about 2 seconds, and they appear as upon the merger of neutron stars. Then we also have long GRBs, which are, as the name implies, much longer. They originate from supernovae, and in fact, most observed GRBs, I think I may be wrong here, but I think more than 70% are actually long GRBs. Another feature associated with these explosions is something that we call the afterglow, which is a series of emissions over spanning multiple wavelengths, like all the way from very high energies like X-rays to low energies like radio, and time scales. So we're talking days, weeks, months, and so on. Finally, as the final product of this, either the result of the merger or the death of a star, could be a black hole, could be a neutron star, stable or not, meaning that could be a neutron star that's relatively short-lived and then finally collapses into a black hole. And one thing that I'm going to talk about, because it's part of our motivation here, is GRB 170817, which is the gamma ray burst associated with the gravitational wave event GW 170817. It was the first multi-messenger observation of a merger of neutron stars. So we had gravitational waves, we had gamma rays, we had observations spanning the entire electromagnetic spectrum. And this figure here, it shows, it's just a scheme of how we believe gamma ray bursts to form. So as the engine, in this case a black hole, powers the jet, so within the jet there are multiple shells of materials. Some of them are faster, some of them are slower, and as these shells are launched and they propagate, they start interacting with the external medium. It's upon those interactions that a lot of interesting physics occur. So these can be interactions between the shells and the external medium, or interactions between two shells. So for instance, you have a first shell that's slower, and then it gets even slower as it's interacting with the external medium and picking up more material. And in the meantime, there's a second shell that's much faster, and eventually they collide. So this leads to shocks, reverse shocks, and formation of there are magnetic fields, which in turn accelerate electrons, leading to synchrotron emission. And as this material interacts with the external medium, there's the afterglow, which is what I just mentioned a few minutes ago, which spans pretty much every single the entire electromagnetic spectrum, and lasts for much longer durations, like days to months and so on. I'm pretty sure this is nothing new here. This is a figure that everyone has probably, or most people here, have seen before. And associated with gamma ray bursts are a series of problems. Some of these questions were answered with GW 170817 and all the electromagnetic observations that followed that merger. But there are still multiple open questions. And if I decide to talk about all these questions here, we would probably need an entire series of seminars just about open questions in GRBs. So since I have to filter things a little bit, I am going to focus on two questions that I'm mostly interested in at the moment. The first of these two questions is the following. What are the objects which are capable of powering the jets that reach the energies that we observe and give origin to those gamma ray bursts? The first answer is black holes. We know they are super powerful. But what about neutron stars? Can they power them? In particular, magnetars. Magnetars are neutron stars with extremely high magnetic fields. We're talking about something like 10 to the 14th, 10 to the 15th Gauss. But are they powerful? Are these magnetic fields powerful enough to help launching those jets? And are these jets fast? Will they survive long enough to actually lead to the formation to the launching of to the formation of gamma rays of gamma ray bursts? So this is one of the questions that I'm trying to answer, and I'm going to talk about this in more detail in a couple of minutes. The second question concerns the origin of gamma ray bursts. We know that there are multiple gamma ray bursts originating from in environments with very low density. A star dies, it explodes. That star is somewhere in the in a given galaxy, in the vicinity of a given galaxy, or there's a merger of two neutron stars, also within a low density environment. But what about higher density environments? For instance, the accretion disks of supermassive black holes. We have multiple reasons to argue that it would be possible for some of these stars living in this high density environments to explode and possibly lead to GRB. So the thing that we are doing here is we're trying to find some kind of signature that will tell us for sure that that GRB that we detected likely originated in a higher density environment. So now I'm going to talk a little bit more in detail about these two projects that I'm working on. This first one is about magnetars and jets launched and powered by magnetars, and the possibility of those jets to generate gamma ray bursts. This is in collaboration with Pablo, Philip, and Davide. So, okay, so why do we want to talk about magnetars, about neutron stars, and engines other than black holes? Well, we've known for a while that the jets that originate from the remnant, they can launch short gamma ray bursts. And indeed, as I was saying just a few minutes ago, this has been confirmed by the multi-messenger observations of this binary neutron star merger, GW 170817 and GRB 170817. Well, that observation, that series of observations, not just the gravitational wave detections or the immediate follow-up observations on gamma rays, near infrared, visible light, whatever, it doesn't matter the wavelength. All those observations, they helped us answer multiple questions concerning neutron stars, gamma ray bursts, and a series of associated processes that occur, like nucleosyntheses, the nature of kilonovae, and so on. Many questions were indeed answered, or in a few other cases, that event was enough to set a series of constraints that helped that help us choose what models are better suited to that kind of data, that kind of events, and rule out a couple of other possibilities. But even though that merger and all subsequent observations and all that series of papers that multiple groups have written ever since have helped us answer multiple questions, there is still a couple of questions that remain unanswered. And one of these questions that partly motivates this work is that there's still no absolute conclusion on the nature of the engine that powered that GRB. Could it be a black hole? Could it be something else, and like a magnetar? And magnetars are actually an interesting proposal for the engine powering this GRB. And the reason, and that's discussed in more detail in this paper by Brian Metzger and collaborators, is that some simulations that were performed up until then, they had some kind of conflict with the actual observations, in particular the observations of the kilonovae, of the blue kilonova that appeared as a result of this merger. I honestly I don't remember exactly what was the main source of conflict here, but I think it was related to the electron fraction in the models that were being used in many simulations. And what Metzger and collaborators found was that if you assume that you have a magnetar with a magnetic field of around 1 to 3 times 10 to the 14th Gauss, you could actually explain what was seen in this series of observations. But even then, I mean, that was not the first time that people have suggested that people have proposed magnetars as a good source of those jets powering the GRBs. A series of relatively recent works, they also tackled this issue. And in one example, this one by Ruiz et al., 2016, they found that it's possible to have jets that when the merger leads to a magnetar, but what they found was that the jets only started to appear after this magnetar further collapsed into a black hole. Another series of works by Chofi and collaborators found that no jets were formed that were powered, that could be powered by magnetars. But one thing to keep in mind here is that they did not include neutrino effects. And although I am not a specialist on neutrino effects, they do play a significant role in the formation of jets. Now, this figure here is from this work.
Can I ask
yes.
Quick question? So for 170817, if the magnetar is proposed as a central engine, do they propose that the magnetar is still a magnetar, or has it collapsed already into a black hole? And if so, how long did the magnetar live?
If I have to double check, but as far as I remember, in this paper, they suggested a magnetar living up to about 1 second. So pretty long. So it lived for a while before collapsing into a black hole.
Mm. And is this for like the other magnetars? How long are they supposed to live? I'm no magnetar expert.
Yeah, I'm not a magnetar expert as well, but yeah, some of them are actually a little bit more short-lived, like 0.1, 0.2 seconds. A few others may live a little bit longer, but in the case of these other papers that I am citing here, I really don't remember now how long they lived.
Okay. I thought they were very long-lived. Not
just a quick comment.
Some of them may be longer lived. I mean, yeah. I mean, when you have those mergers of neutron stars, they can, collapse into a black hole straight away or live as a relatively stable neutron star, as a fully stable neutron star, so no further collapse, or they might also become like a neutron star, but it's unstable, and then they further collapse into a black hole within short or within a short period, or sometimes a longer period. But if I'm not mistaken, I think most of these works that I'm citing here, they are actually quoting, they are actually having magnetars which do not live for that long. So in this case, in particular, this paper that I'm going to discuss a little bit more in detail, it lives for about 1 second or so. Someone was going to ask something. Sorry.
Sorry. Yes. Sorry, Albert. I wanted to make a quick comment going back to what you were discussing earlier. I think, just so that we're not confused here, many people that discuss objects, that lived only for a short amount of time, they were discussed in the context of, if I remember correctly, hypermassive neutron stars. They're very short-lived objects,
yes.
not per se magnetars.
Yeah.
Because when we discuss magnetars, we're generally talking about stable neutron stars with strong magnetic fields, which are going to stay forever, right? They don't collapse.
Yeah.
So most of the models that do exist in the literature discussing magnetars are, I think, only discussing stable neutron stars that are going to stay forever. But in the case of GW 17 most of the discussion was about this intermediate object, which eventually collapsed to a black hole. And then, of course, the black hole powered the subsequent jet. But then, of course, in that context, it would be either, it would be most likely a hypermassive neutron star, which is a quarter second or so. That's the likelihood, right?
Yeah, that's correct. I mean, when I'm talking about magnetars here, I'm pretty much implying it's a hypermassive a neutron star with an extremely strong magnetic field. So yeah, but thank you. That's correct. Yeah. So yeah. And this problem has been further investigated by Philippe Mussa and his collaborators back in 2020, and they studied, they used some very high resolution, and by very high resolution, I mean adaptive mesh refinements, GRMHD, so general relativistic magnetohydrodynamical simulations of neutron star merger remnants. So that was a very interesting series of simulations. Actually, they started out with the actual merger with dynamical relativity. So they actually had the two stars merging, and upon this remnant, they took that data from that simulation, they mapped that data into another simulation where they added a very strong magnetic field, and then evolved that simulation for a little bit longer. That object, that magnetar, that it released a jet before collapsing into a black hole. But one key difference between this work and some other previous works was that they paid more attention to two things, which are the nuclear equation of state and neutrino effects. And neutrino effects, they matter because they may they help preventing like baryon pollution at the at the polar regions of the remnants. And this figure here on the right, that's taken from their paper, and it does show they actually had a series of simulations. So this is one of their simulations, and here we see top to bottom the density, the temperature, baryon number, and velocity, and the plasma beta, the ratio between the magnetic and gas pressures. And they found they had some very interesting conclusions to their paper. They managed to reach some very strong magnetic fields. I mean, part of this is, it's something that they started from. So they had magnetic fields of around 10 to the 15 Gauss. Their outflows, they had both magnetized winds with, they were mildly relativistic. So in some cases, we would have velocities going up to like 0.5, a little bit more, but usually they were around 0.4 C. And jets with a maximum Lorentz factor of varying depending on the simulation, 2 to 5. So it was a set of simulations where in one of them they had neutrino effects, the other one they didn't have, another one they had this nuclear equation of state. But Philip told me that they are doing a series of other simulations where they are adding more detail to their models, especially the parts concerning the equation of state. But the key thing here, and they also had an ejecta that was roughly 5 times 10 to the minus 3 solar masses. But the key thing here is that they found evidence that object, that magnetard, could indeed power those jets and those gamma ray bursts. But one price that they had to pay to do this very high resolution simulation, like very detailed, is that they couldn't really propagate their jets for their outflows for very high distances. So the snapshot, these photos these pictures that I'm showing here, they are pretty much their entire domain. So this is still a relatively small spatial domain. So, and those jets, we know they propagate to distances much longer than this. So in this work that I'm presenting here, what we did was we took their data and we extended that propagation to further investigate how the jet behaves in this context. And we also ran in parallel to that another simulation where we added, instead of what I call real data, which is the simulation data, we start that simulation with a top hat model. So following basically a jet that originates according to a series of equations that determine its profile. So this is what I'm going to talk a little bit more about now.
A quick question, Gustavo, if I may ask.
Yeah.
If you go back to your previous slide, could you briefly comment on what is the main mechanism that is launching the jets? Is it, I mean, you also mentioned neutrinos there, but is it all Poynting flux dominated emission, as you would expect in a black hole?
Yeah.
Are these different?
Yeah, it's Poynting flux dominated. So yeah.
So is it something similar to a Blandford Genaic? I mean, do we understand what that is?
Yeah, I believe so. I believe it's similar to Blandford Genaic.
Okay.
Sorry, if I may ask, so are these short or long GRBs?
Yeah, these are short GRBs because they are, yeah.
So are you assuming that so this must have been, if you are going to use something like Blandford Genaic, it should be like millisecond pulsars going into 1 second pulsar or something like that. Otherwise, I don't think you would get close to the necessary energy. Is that right?
Yeah. So this object, so I have about 40 snapshots that's from the moment that the jet is launched. Sorry, at the moment that the jet reaches the end of their computational domain until that object collapses into a black hole. And those 40 or so, like 38 or so snapshots, they are spaced, they were generated within 0.015 milliseconds of each other. So yeah, my time frame here is 0.04 or so seconds. So it's still a very, it's pretty small.
Okay, it's just that from what I can recall right now, in Blandford Genaic, you usually need spin parameters. 0.3 or something like that, and I don't think you can get those with a magnetar or with a neutron star, any kind of neutron star, before you start shedding. It of course depends on the equation of state, but it's not very likely that you can get above that. So yeah, it's
Okay, yeah,
in that direction.
Mhm. Yeah, I don't remember right now. Yeah, I would have to ask Philip about their equation of state in particular, and about any possible spin of this object. I honestly don't remember right now what they had.
Okay. All right. Thank you.
Okay.
Uh,
Yeah.
Excuse me, Gustavo. Sorry.
Yeah. Go ahead.
Is the okay? The initial sorry. The you avoid the pollution of baryonic material over the axis, the Z axis. Is this due to the initial distribution of the material, or is the effect of rotation?
I don't fully know how to answer your questions, but I believe that all those things actually do play a role here. Yeah, I'm not really a specialist in neutrinos. I am actually more interested in the emission itself, which is the next step in this project. But yeah, I don't know if I can fully answer your question right now.
Well, it could be due to magnetic fields. Since you have strong fields, that would tend
Yeah,
to.
strong fields, yes. Yeah.
Okay, thank you.
Yeah, so yeah, for this this simulation, we use the code Pluto, which I know some of you are very familiar with. We set up our grid. This is a relatively high resolution, so we have 437 by 437 cells in the X and Y axis, followed by 837 cells in the Z axis. This is a Cartesian grid. It's not adaptive mesh refinement yet, because I'm still not fully familiar with Pluto's adaptive mesh package, but we do highly concentrate ourselves in the center. And by center, I mean the region where we are injecting that data. And we keep the same, in this central region, we keep the same resolution as Philip had within one level of adaptive mesh refinement. Our model, we have some ambient density and pressure, and we have this semi-spherical stellar-like material, which is part of the ejecta that decreases exponentially as we go further away from the center. And yeah, so what we see here is on this figure on the left is it's the density profile, you know, a top bottom view of the density profile as we start our simulation, as we inject the initial data. And speaking of this, speaking of mapping data, as I was saying before, we have roughly 40 snapshots separated by 0.015 milliseconds from each other. And that's, you know, when the jet reaches the outer limits of the original simulation box and before it collapses into
Gustavo,
the storm collapses.
quick question, only for curiosity. How long it took for you to run the simulations? Because I know that 3D simulations can be costly.
Yes, a month or so.
Oh,
Yeah.
and like in a cluster?
Yeah, in a cluster. We use a cluster. We use roughly 400 cores, but we had some issues with like fine-tuning some parameters for our simulation. Like the CFL number was a big problem. We realized early on that we had to use a relatively a small CFL number, otherwise the simulation would just crash the problem of choosing a small CFL number is that it would it made our simulation run much slower. But yeah, it took roughly 4 weeks or so until we finished running the simulation.
And how small is small for CFL?
Yeah, so we started a little optimistic with something like 0.3, 0.4, but we quickly realized that it would have to be around 0.05 or so.
Okay, yeah. And then
Yeah.
another question is, do you simulate the whole sphere or just like an eighth of the 3D?
No, it's just the bottom, the top half.
Okay.
Yeah, so we just have like one jet propagating upwards. And well, yeah, talking a little bit more about the injection procedure, since we don't really have a lot of snapshots, we don't really have a lot of data to inject. And I feared that could not be enough material for us. So what I did was, after I finished injecting the 40 snapshots, I restarted the process. So it's a constant loop of injections just so that we have more material. Yeah, and the quantities that we mapped are the usual quantities in most of these simulations, like density, pressure, velocity, the 3 components of the velocity and magnetic field. This is not a GR-MHD simulation. It's not general relativistic, but it's an RMHD simulation, so relativistic magnetohydrodynamical simulation. And this is a video that shows the evolution of left to right, the pressure, the density, the pressure, the velocity, and the plasma beta, the ratio between magnetic and gas pressure. So let me see if it's going to play. Yes, it is. So this is how the jet evolves. And there are multiple interesting things that we can find here. So the first thing that I noticed, well, there are actually many things that I noticed right on, but they include the appearance of shock fronts. I'm going to talk a little bit more about this in the next slide, but also the velocity increases to roughly 0.7, the maximum overall velocity. So this is very nice for us, because that means it's the jet is picking up speed, but the jet also, as you can see here in the velocity plot, in the very middle of the plot, we can see how the jet kind of like is a little choked before it picks up velocity again. But if you pay a little bit more attention, you will see that this area where the velocity decreases is very correspondent with the shock. So I think this pressure plot here shows the shocks really well, but I think it's even better if I switch to this, because so on the left we have the density, on the right we have the pressure, and here in the center, please ignore the y-axis quantities. This is a different scaling, so this plot is actually still some work in progress, but this is a profile along the jet axis. The jet is a little bit tilted. I don't know if you could see this from the simulation, but this is extremely normal for jets. But what I'm showing here is the reason why I made this this profile plot is that I wanted to see how these quantities were behaving along the jet. And here I think it's very clear that we can see the shocks, and they are indicated by these two arrows. So roughly around 4 × 10⁸ centimeters, we have one shock, and we can see this sharp, sudden increase in pressure and density, but also a sharp decrease in velocity. And then a little bit later, at 5 or so, 5.5, that's when the velocity starts to pick up again, and we can see this on the bottom plot here, which is the Lorentz factor. So it's top to bottom density, pressure, and Lorentz factor. And close to the very top of the jet, we have another very interesting shock appearing, which is related to the interaction between the jet and the external medium. And we can see this sharp increase in density because the jet is picking up material, and also see that the velocity is increasing. So that corresponds to what I showed on the video, which is the jet picking up speed again. One thing that's still missing that we are working on currently is the magnetic field profile. We are working on, we're making plots of the magnetic field lines to better understand the behavior of the magnetic fields, because this is fundamental to understand the overall dynamics of our jet here. But
Sorry.
yeah.
So I have actually two. But so how is your initial dense is the magnetic field lines? Is it colloidal? Is it toroidal?
Yes. So the original simulation was a purely toroidal magnetic field.
And you also put the distribution in Pluto, or?
Yeah. So in the ambient, I am assuming a very small magnetic field, mostly to avoid any kind of possible numerical issues. The magnetic field that appears here is what I am injecting from their data as they are. So the three components as they are. I'm not making any kind of assumptions here.
Okay.
Do you know what the magnetization is?
Not yet. I'm working on this right now. But if I assume this to be high.
High. Okay.
And why is the jet going towards the left? Is it the jet condition, or is it the ambient medium density pressure, or the magnetic field? Like, why is it?
It could be some instability in the jet itself that makes it wiggle a little bit. But the thing here is that I don't know if this behavior of going to the left will actually it is how real or how artificial it is. And that's because I am injecting the same things over and over and over again. So because we don't really have in too many dense snapshots, it could perfectly happen that further, like if this thing survived for much longer, if we had a longer lived jet, meaning a longer lived object, meaning perhaps a longer jet with more snapshots, it could be that it would go back to like shift a little bit back to the right.
But if you inject an axisymmetric jet, even in 3D, it would be axisymmetric. It would only go upwards.
Right.
Yeah,
So
but
unless you're putting some variability in the jet velocity, launching angle, then yes, it would go to the left. Or it could be that there's some turbulence or some variability in the ambient medium pressure or something that makes the jet go left. But if the ambient medium was perfectly smooth and the jet was perfectly launched vertically, it should go vertically, even though it's in 3D.
Yeah, so this jet, it's launched from the accretion disk in their simulation. So it's not a model that you just describe a profile and your jet will go up. And you will see actually that the next video that I'm going to show is this top hat model, and you will see very clearly the jet going up.
Okay.
So
I'll shut up
think,
and let you.
No, it's fine. I mean, I think this is due to turbulence. This is due to perhaps some kind of instability, but I think this effect is increased here in my simulation, because if I already had a couple of snapshots where the jet was just slightly tilted to the left, since I am injecting the same thing over and over and over again, I'm not going to correct this behavior. So even if it's, so I think this is some artificial thing that's partly due to the way that I am injecting this data from their simulation.
Okay.
But yeah, so the equations appeared before the text. Okay, so the top hat case, which is the second jet that I'm going to show here, it has a very similar setup. So similar, same initial conditions, same ambient conditions, same material. The jet is modeled according to a top hat profile that I think it's pretty much a standard for many groups. Mignone, Gottlieb, they all use the same profile. And this profile is as follows. So we set a radius, which we call R0. In our case, we set R0 to be the radius of the domain where we injected the jet in the previous simulation. And then we just assume a density that's smoothed out radially. By radially, I mean in the XY plane. And by this profile, which is 1 over the hyperbolic cosine of R over A, where A is half this R0. People usually set this to 1 in their papers. Here, this R0 is actually 0.21, or yeah, it's the size of the physical domain that we had our jet in the previous simulation. And then we have the magnetic fields, which are given by this very complicated set of equations. Here in our case, we chose a purely toroidal magnetic field, which is given by this parameter sigma phi, and we set this to 1. This is higher than what people usually do, and the reason why I chose this is that as I was testing some parameters, I feared that if I had used something like 0.01, like some of these groups use, or even 0.1, I was not sure if I would have magnetic fields that would become as strong as I was hoping they would. And so I had to, like, this is a free parameter that I had to give myself some liberty to choose and go a little bit beyond what people generally do. And I also injected this jet with an initial Lorentz factor of 1.1, which corresponds to a velocity of 0.4, which is an average velocity that we had in our previous jet. So I tried to match as much as I could this guy to the previous one. But I know that it's not going to be perfect because especially the magnetic field part, it's highly dependent on your models and your parameters. But the other quantities like pressure, jet density, and velocity are as close as possible as what we had in the previous case. So this is the simulation, and the jet does reach a similar velocity as the previous one. It appears actually to be a little bit slower, but not by much than the other one. But as we were talking just a few minutes ago, you can see the very clear profile of this jet going all the way up, not tilting or anything like that. The jet is also very highly collimated, in part because of this higher magnetization that we chose. The plasma beta here is a little bit higher than what we had before, so maybe I could have chosen a slightly smaller magnetization parameter. But overall, we also see this shock here, which is something that we were looking for because you know it's the shocks that matter the most for us. Eventually, we do want to propagate this for even longer distances and study the shocks in more detail to hopefully do some kind of radiative transfer to see what spectrum we could expect. So if I put those two simulations side by side, there's this very clear difference in the magnetic fields in the beta profile, but that was expected because of how we set up our simulation. We had to pick a set of equations to determine how our magnetic field was going to behave. But and this is something that we are currently investigating to look for further to lead possible similarities, but also differences between these two kinds of models. But overall, we do have some features which are similar between both simulations. These quantities like densities and pressures, they are just as expected because, well, we injected those guys to be with that, to have those values. So that's not surprising. The velocities, I was quite happy to see that both achieved similar velocities. I had no idea whether this was going to happen. I actually, for a while, I even thought that the top hat was going to be a little bit faster because of stronger magnetic fields that could help make the jet go a little bit faster. But indeed, there's this very different magnetic structure that we are currently investigating. So right now, I cannot comment a lot about this in particular. So the key points from this this project so far is that the magnetars do seem to be capable of powering those jets. We have this was already seen from Philip's paper, but the jets are still going strong here. We see the shocks appearing. We have the jets speed up a little bit, so we reach velocities of 0.7. We do have a strong magnetic pressure. What else? And yeah, it's the shocks that I'm mostly interested in, and something that I want to investigate further down once we were able to propagate this for longer distances and do some kind of radiative transfer. But this is follow-up work. And the top hat model, it does have some agreement with real data, but it's still very highly dependent on whatever prescriptions you choose. So I believe this could be a source, perhaps, of some issues in the future. Like depending on how you pick your parameters, you could have some vastly different results. And as I said before, we are working on the magnetic field lines at the moment, so there should be something. I do expect to have some plots ready by sometime next week. Yeah, with this, I finished this part, and now I'm going to talk a little bit about GRBs in dense environments. This is a work with Davide and Rosalba and Stony Brook. This is a shorter part of this presentation, and some motivation is a series of recent interest in this possibility. So we have reasons to believe that stars do exist in the disks of AGN, either due to some kind of instabilities, like gravitational instabilities in the outer regions of the disk, or stars they live in a surrounding cluster that's nearby, and then it gets captured by the gravitational potential of the supermassive black hole. So the star eventually goes to the accretion disk and lives there for a while. But there's this recent interest in the evolution of stars in these environments, and these two works by Matteo Cantiello and Dittman from 2021, they do a series of analysis of what could happen to those stars, and in particular this work by Germain, I think it's very interesting because what they found is that some massive, many stars living there, they end up being very massive and fast rotating stars, which are very promising candidates for long GRBs. So, I mean, this doesn't really exclude short GRBs, because we could still have mergers of stars happening within those regions as well. And since we are talking about an environment that's very dense, the interactions between the outflows of exploding stars or merging stars, they're going to interact with that environment, and those interactions could lead to some drastically different signatures. Some transients that we might detect that will be rather different from that could be rather different from what we are mostly used to, or maybe we have already detected, but we don't really have the means to properly identify and classify those guys as having occurred within that region. Or perhaps, I mean, there's also the possibility that The jets will just be choked like a failed jet, and there will be no visible radiation that we can detect. And but anyway, there are some factors that may also influence the final outcome of this kind of system. They include the location within the disk. So there are some works, especially one by that's very well known, the TQM paper by Thompson, Quaitert, and I forgot who the M is. But yeah, anyway, they map the profiles along the density and pressure profile of an accretion disk. It's a model. It's not extremely detailed, but it does have some interesting features, like how the density may vary along as you move outwards along the accretion disk. Also the effects of the supermassive black hole mass and the disk mass as well. All those things can lead to possible different outcomes, which could include jets or no jets at all. So in this work in particular, this is a work that's being led by Davide and will be followed by a set of simulations that I'm running. But in this work, what we want to do is basically we're asking ourselves, okay, what are the features that we can identify of this prompt emission when the jet, is born in this very high density environment? And the other question is, upon looking at those possible features, are we going to be able to identify, something that's unique to those guys, something that will make us say, okay, this guy, when we observe something, when we detect something, we can say, okay, this very, very likely happened within a dense environment because of this, and that. And to answer this, we do here some a semi-analytical analysis that I'm going to explain now. I'll start with some qualitative considerations, and then I'm going to follow this with our model, and then some results. So, like I showed on that very first picture, that cartoon, the prompt emission is due to either internal shocks between the shells, or it could be the interaction between the shells and the outer medium, or perhaps some combination of both. Now we have a high density environment, which means that the leading shell, since it has to deal with a higher density material, it will start decelerating early on, because it's, well, there's something big that it has to try to go through. Now, if this deceleration occurs before the shells are starting to, before the subsequent shells start to interact with each other and collide with each other, then we have enough time for them to, for these shells to catch up and interact with this external shell. And this is what we want to do here. We want to slow it down and then have the second shell go and hit this first shell. Also, we have a central engine, a black hole, for instance, that will produce those shells within a constant, like they are similar to space. They have the same thickness. They are produced within the same interval. And what we're going to see here is that the pulses will overlap a little bit with each other, and that will lead instead to a light curve that's like this, like different pulses. It's going to be a broader overall pulse. And also, as we are going to show here, as we're going to confirm this, if you have the engine that releases a couple of shells and then powers down, cools down for a while, a couple of seconds, like 5 seconds, 20 seconds, and then it powers up again. So unless there's this substantial dead time between these shells, where we don't really expect to find a multi-peaked curve, again, because like I said, these pulses will be released within a short time between each other, and they will overlap into a single broader emission event. And since we have a higher density environments, the effects of synchrotron self-Compton will likely be important. This is the final thing that's missing in this paper. It's something that we are working on right now. So our analysis basically extends those qualitative considerations. I'm not going to show all a set of equations because it's going to be very boring, and I don't think it's very helpful, but once the paper is out, you will see how we set up this problem. We have a central engine, which is within this medium with a density of 10 to the 12 per cubic centimeter. So it's a higher density medium, the ISM, the interstellar medium. And then we have a bunch of shells. Actually, here we do in sets of 5. So we will inject 5 shells. Five shells are launched from this central engine, all within a same regular interval, which we take to be 0.5 seconds. And their thickness, that's this delta T that appears here, and their thickness is governed by precisely this. And they will all, we assume that all of them will accelerate to the same Lorentz factor. So in other words, we are launching identical shells. The first shell, as it's going to interact with the external medium, it will sweep up that material and decelerate in the process. And it starts decelerating at this radius that we call RES, which is the radius where the external shock happens. And then this radius, we assume we take it to be smaller than the internal shock radius, RIS, meaning that the first shell will interact with the external medium and shock there before the second shell catches up. So as the external shock is evolving, the second shell will catch up at this collision time that we call T-call. And this impact will create an emission spike. That's where things start to matter a lot for us, because that will give rise to a short transient event, and then there's going to be a reverse shock that will propagate backwards into the shell. This is pretty much the standard shock theory. Oops, sorry. Yeah, and well, the thing is that this impact between the second shell and the first shell that just interacted with the external medium, it will re-energize the external shock for at least for a while, until it cools down and returns to its own self-similar solution. But in terms of our code here that we use for this analysis, that just means that we will have to run the same equation again, but with slightly different quantities, because in this case in particular, it's going to have picked up more mass. And well, subsequent shells, as they reach the first few shells, they will produce a similar effect. But the key thing about the reverse shocks that form upon the collision between two shells is that they can lead to GRB formation. That's because the electrons will be accelerated to a given internal Lorentz factor, which we call gamma int. And we're going to have magnetic fields, and that's a perfect scenario for synchrotron emission that will peak at this observed frequency that's given by this equation. And with this setup, so I mean, behind all that I said, there's a bunch of equations that we cannot solve using our bare hands, but we can write a short computer program that solves this system of equations. So, and this is what happens here. These two figures, so they show, let's focus on the left figure for a while. Here, we're not showing yet the synchrotron self-Compton contribution. So bear in mind this. But we have in orange, we have the peak frequency. In blue, we have the light curves, and those thin black lines are the pulses from the shells as they interact. So we see very clearly how it's like here on the left side of this picture, how they are not how it seems to form this continuum light curve rather than a peak from the first shock, and then it goes down, and there's another peak from the second one. They're all like those little peaks, but it never like, there's no cool down of sorts period. And that's one of the main things that we see here. And on the right, we do the same thing, but we release those 5 shells within 0.5 seconds of each other. And then we give the engine a cool down time of 5 seconds, and then we release another 5 shells. And that's what we see here on the right. So we do have the first few, first like peak in the light curve, followed by the second peak from the second set of shells. And what if we make it, what if we pause this engine for an even longer time? That's what we see here on the left. Instead of a 5-second pause between turning off the engine and then turning it back on, we have a 20-second pause. And again, it's a very similar behavior in the light curve, but interestingly, we see that the peak frequency actually, after a while, it will increase from the second shell. And I'm not sure we fully understand why this is happening. This is some work in progress that and we are currently discussing why this could be. But here on the right, we see the Lorentz factor of the external shock as these subgroups of shells are interacting with it. So we have here these tiny increases from, you see very clearly the shocks and the sudden increases in the Lorentz factor of those regions, followed by the second shell. So we do hope, so this is still a work in progress, but we do hope that these features in the light curves will help us will give us like a better idea of what we could expect from such an environment, for such an event happening within this environment. But this is still a work in progress. And this we're also doing parallel to this some very simple shell simulations of shell collisions. So here I assume based on that TQM model, I assume this density in the ISM, and this is followed by some. So what we have here on the left is the injection of the first shell with top to bottom. We have pressure, density, pressure, and Lorentz factor. So we have this first shell with an initial Lorentz factor of 30. It has a thickness of 10 to the 11 centimeters, and the gas density here is around 10 to the minus 6. And then in the middle panel here, we have it's just zoomed in, like the sizes are still the same. I'm just zooming in, but that's where we inject a second shell, which is faster. So a Lorentz factor of 300. It has the same thickness of the first one, but it's also less dense. And we are basically evolving this system to see how the jets, the shocks will form and what are their main features. And some of this can be seen on the right panel here, where we can see here at the very tip of the shock front, we see this little increase in the density. That's as the shock is picking up more material. We also see the shocks appearing. That's very clear on the pressure plot here, in the middle on the right figure. See that sharp increase in the pressure that's due to shocks as well, and we see the evolution of the Lorentz factor as well. But this is still a work in progress that we hope to add a simple radiative transfer model to check like frequency peaks and eventually come up with a light curve. But in this case here, we only have two shells. So the initial shell that's first interacting with the external medium, and then the second shell that catches up and interacts with it. We don't have like further shells. We don't have the engine pausing for a while, then releasing more shells. This is a very simple case, and we do plan to vary some parameters like the external medium, because depending on where you are in the accretion disk, your density profile will change a little bit. So we want to try multiple different scenarios here, but this is our current work in progress as well. So the key points from this work is that we do have some individual pulses that, since they are separated by a short time interval, we have a kind of a continuous single envelope, what we call a continuous single envelope merger, and we also have some one thing that we can say is that since the later collisions, the later collisions, they are leading to longer pulses with a lower peak frequency. We can see this here in these this series of plots here. So that suggests a hard to soft spectral evolution, but we're still going to make a full plot of the spectrum to have a full understanding of this behavior. And as a work, we have this work in progress, which is a series of simulations of these shocks that we eventually plan to release as sort of a companion paper to this one. But that's something for the next couple of months. And yeah, with this, I finish this presentation. And if you guys have any other questions, I'm happy to answer.
Thank you, Gustavo. So raise your hand, whoever has a question. I have one, but I don't want to own the microphone. So. Okay, so well, someone asks something else. My question is, Gustavo, so in your first study, they're saying slide 12, if your simulate, I didn't understand, like if this magnetar simulations are motivated by 170817, why is the Lorentz factor that you choose so low?
Yeah, so they're not. Yeah, they are motivated, but the thing is that the velocities that they achieved here in their jets are relatively, in their outflows are relatively low velocities. It's a mildly relativistic outflow that we found here. So I am not sure if this will surely explain that particular case of 170817. It's more like saying, okay, it's possible for magnetars to power those jets, but the low value in my velocity was basically that I chose for my next simulation as well. It's something that I chose to match the velocities that I was having here in this real data simulation. So I think the main conclusion is that magnetars are capable of powering those guys, those jets, those GRBs, but I'm not sure if this answers the particular case of GRB 170817. That's something that I am not going to claim here. I'm not going to say, okay, that guy was a magnetar, that jet was powered by a magnetar. Right now, I can't answer this.
But all GRBs, short or long, have Lorentz factors larger than 5.
Yeah, exactly. And here it's something that it's one of the reasons why we need like some, I think we need some higher some to propagate this for longer distances, because we started with something that was c, like a velocity of 0.4, and now this increased to 0.7, and I wonder, okay, can we increase this to even longer as we propagate this through longer distances? Will this jet pick up more pace and become faster and reach Lorentz factors similar to the ones that we expect? I think it's possible. I mean, if I print you know, the velocity, the Lorentz factor, in some cases, in some particular points of the simulation, I will find some very high Lorentz factors, but it's not the overall thing. So that's one of the reasons why I want to run this for longer times and longer distances, because I agree with you. I was like, okay, when I first saw Philip's paper, I was like, okay, but they say velocity of 0.4, and the first thing I did was like, okay, what's the Lorentz factor of this? And I saw, okay, it's 1.2, around 1.2. That's very low. That's not something that I would expect.
You could even use an MHD code and not RMHD, like the relativistic part would
Exactly.
be necessary.
Exactly. Yeah. But now that I'm seeing this velocity increasing, and AKA the Lorentz factor increasing, I'm thinking, okay, is our problem just one of not running this for longer distances, or is it going to die out like this? I mean, it could be that in the end, they will not be powerful enough, those jets. So it's still a possibility. But again, I really think we would need this to evolve for longer distances to have a full answer to this question. But it's something that I am a bit concerned as well. Yeah, we have a raised hand. Oh, sorry, did I answer? I think I'm muted.
Go ahead, Ramandeep.
Hi, so yeah, follow-up question to what Diego just asked. What is the injection time in the simulation that you show us on this slide? What is the jet injection time, and how long are you planning to extend that?
Yeah, so the injection here it's artificial in the sense that it's constant. So the whole simulation, I am injecting material. And this is just because I didn't have enough snapshots, and I wasn't sure if just 37, 38 snapshots would be enough to study this evolution in more detail. So we have two plans now. The first, this is entirely on Philip's and Pablo's side. They are running simulations with different equations of state. I admit I'm not really a specialist on equations of state, so I don't know what changes they are making, but they say that they could have jets that propagate, they could have a longer lived object, and therefore a jet that lasts a little bit longer than what we have before the object collapses into a black hole. So this could in turn allow us to just inject their material and let the simulation go, instead of, you know, looping this injection over and over again.
So yeah, that's my point here. Because these, as you're trying to simulate hypermassive neutron stars, these are, you know, short-lived for over less than a second, or sometimes even, you know, 500 milliseconds, half a second basically.
Yeah.
So that's, I mean, so what is the injection time in your simulation? Is it longer than that, shorter than that?
Yeah, so each, so the snapshots that we inject here, they are separated from each other by 0.015 milliseconds.
Okay.
So the original injection, like what we have is 40 times this, so around 0.015. So yeah, it's a very short injection. But since we do this continuous injection, because we don't really have too much material to work with,
Right.
in practice, the injection is the whole time of the simulation, which we know is not ideal. It's not what we would expect in nature, but this is something that we felt we had to do in order to perhaps have a jet that would lead to some, that would allow us to do some kind of analysis.
Right. So the point, then the problem is you're limited to, half a second or at most a second time scales. And in such a time scale, can you achieve high Lorentz factors? That's
Yeah. So and that's that's where we have this problem, which is a computational problem. Since ideally what we would do here is some kind of adaptive mesh refinement simulation, because we hope that this would allow us to have not to concentrate resolutions in spaces where in areas where it doesn't matter. And if we can just focus our resolution without using this artificial method that I use to just insert a bunch of continuous cells very shortly separated from each other. If we have this adaptive mesh grid that we hope will save us some significant computational time. And if that will save us computational time, that means we can evolve this guy for much longer. And if we evolve this guy for much longer, I mean, for as long as our computational capabilities allow us to evolve this, then I really do expect this to achieve higher Lorentz factors, and therefore be make a stronger case saying that, well, yeah, these guys can indeed power those GRBs. But as we see here, the simulation runs for 0.07 seconds. So yeah, it's a very short simulation. But unfortunately, we have to deal with these computational constraints that we hope to find a way around this by using adaptive mesh refinement.
okay. Very quick final question. So you're using Pluto. Are you at all limited by how much magnetization you can have in the flow in Pluto? Because for example, I'm familiar with Gottlieb's simulations, and then he didn't carry out those for high magnetization flows because he uses Pluto, and then he had to switch to other codes, I guess. So do you know, is there a limitation with Pluto of how high a magnetization you can have?
I don't know, but I suspect there is. When I was preparing these simulations and doing many short runs, trying to gauge the best parameter set, I would sometimes change a little bit my magnetizations and find that my simulations could crash, my jets would look weird in some cases. I remember if I used this very same magnetization, but a even slower jet, the magnetic fields would just crush the jet and there would be no jet. So I think that if I increase the magnetic fields, I could have something similar. I could also have some numerical issues as well. But yeah, I can't say for sure, but I suspect based on a couple of tests that I did that this could indeed be the case.
Okay, thank you.
Let me just add to that Ramandeep and Gustavo, my student Leonardo, who is actually the organizer of these talks, also uses Pluto with beta parameters of like 0.1, something like that, and the relativistic version of Pluto, and yes, and Pluto doesn't work very good with high magnetizations. Yeah, it's more unstable. So
yeah,
I feel your pain, Gustavo.
Yeah, I mean,
yeah,
Pluto is a relatively new code for me. I still have some unpublished work, some PhD leftovers that I plan to work on as soon as possible, where I was using HARM, which is a GRMHD code, and then there we have fewer problems with very high magnetic fields.
Yeah.
But yeah, it's one of the reasons why I chose that parameter for my magnetization in the other simulation, the stop hat simulation. like sigma equals to 1 is that I remember reading the papers of Gottlieb and other groups, and they were always like 0.01, 0.1, and I was thinking, okay, but will that lead to a magnetic field that is as strong as I want it to be? What if I try sigma equal to 1, and which is what I did here, but I think this is very close to the limit. It could even happen that if I evolve this guy for just a little bit longer, my simulation will just crash. It's still possible.
So Felipe,
I'm sorry, I'm not used to GRB simulations, so I have a question that might be a little bit silly. But as Diego said, your simulation didn't hit, like you had a really low Lorentz factor. And what are the constraints on the energy? I mean, why wouldn't you only increase the kinetic energy of the source in order to reach the Lorentz factor you want?
Okay, so I mean, this top hat simulation, my goal with this simulation was the following. Can I find a set of parameters that matches as much as I can this other simulation where this jet appears in a more natural way? So the difference between these two types of outflows is that in the top hat simulation, I basically have an equation that determines how the jet is going to look like. That's all. That's how the jet is formed. I have like God powers and I say, this is the jet, let there be a jet here. This simulation here that I'm showing on this slide, which is the simulation by where I inject data from Philip's simulation. I'm doing precisely this. I am injecting something from someone else and that jet appeared. It's what we have. So it's what appeared after they had their own simulation, their own accretion disk that led to the formation and launching of this jet. So
Oh, okay.
my hands were a little bit tied in this sense
Uh-huh.
because I depend on what they give to me. So if they give me something that's more powerful than this, then I can play around a little bit more with this other simulation, these parameters, and say, okay, I can assume a higher velocity, a higher speed for my I am God jet, like I can inject something already with a higher velocity. But here it's true. I mean, it's a very low speed, but I mean, I got that. Basically what I did was, okay, let me find a mean. Let me determine what the jet is in Philip's data, and within this data, let me find, okay, what's the mean velocity within this small area here. And it was like, oh, it's this. So that's what I'm going to assume for this other guy here. So yeah, my hands are tied in the sense that I'm just trying to see how these top hat models will be able to match a full full jet in the sense that it was not artificially produced. I mean, this is the third simulation in this set. So it starts with two neutron stars orbiting and merging each other. And then Philip took data from that simulation and added some very strong magnetic fields, and then let that system evolve and generate the jet and eventually collapse into a black hole. And then their jet reached the very top of their simulation box, and I'm picking up from there. So,
Okay.
yeah.
Okay, thank you.
Sure.
So let me stop recording because sometimes some students prefer not being recorded.